Welcome back from the long weekend and all that, and to the end of your very long Tuesday. So I'm joining you again for the next few weeks to do units 6 and 7 here. So you've just completed computer algebra systems. If you remember, I did unit 4 earlier. And we're going to do unit 6 and unit 7 now. So this unit's about using randomness to perform simulations and things like this, do mathematical modeling. Unit 7 starts talking about how to like ingest interesting bits of data from different places and start analyzing it. And then in unit 8, we actually start like trying to do some basic machine learning on those data sets that you're ingesting. Okay. So you've just finished project 1. Project 2 is sort of open. Just for your sort of awareness, I don't have much to mark to do with marking project 1 and project 2. So you can ask me things, but I might not know all the answers. But I am familiar with the projects, obviously. And most of the content you need for project 2, well, we won't get through all of it today, right? So on Monday, when we have a 2-hour lecture, at the end of that, you should be kind of well placed for doing all that work in unit 2. But of course, there's time now and Prax and Blackboard and all those things, so you can start. And the earlier parts of project 2, you can kind of attack probably without waiting till Monday, right? So as you've probably noticed, the course can be a bit busy at times. So if you get familiar with what's in the project, you'll sort of know what to get out of the lectures and vice versa. So yeah. Excellent. So like I was just saying, we're down here October 4. So the next few weeks, I'm going to cover this week and next week, unit 6, and then unit 7 next week. And Yoni's going to come back and do the very tail of the course with the machine learning. Okay. So unless there's any questions, I'll just go straight into this. So you've done computer algebra systems. So we're going to do something kind of almost the opposite. We're going to start dealing with randomness and simulating with random systems with randomness. But in the first unit, first part of the unit, we're going to talk about how you make randomness on a computer. And actually that involves quite a lot of number theory and things sometimes, right? We're not going to go deep into that or anything, but I'll just point out like how computers can generate randomness, or more correctly, pseudo-randomness. So something which seems random, but is actually deterministic. Okay. And then we're going to use this to do a sort of style of simulation or even calculation called Monte Carlo. So Monte Carlo is actually the name of a place in Monaco with a casino, famous casino. During the World War II, when they were building the nuclear bomb, they realized to build better bombs, they would need computers, and they started building computers like ENIAC and stuff. And then during the late 40s, I think it was the physicists and mathematicians like Ulam and von Neumann and Metropolis sort of came together and did some work and produced a really famous paper about the Monte Carlo method, which was a code name they used in the military facility for the project, because Ulam's uncle happened to gamble at this casino and they needed some word to describe to themselves what they're doing, and they chose Monte Carlo as the code name. So, I mean, some of the concepts there weren't new. The fact that you could, like, if you have a statistical problem, you might start with, like, you might draw from a distribution and then, like, solve a PDE or some kind of equation from random initial conditions, right? So, like, people in physics knew about entropy. You know, you have, like, an ideal gas in a room and the things start in random places and then they bounce around off each other. And on average, you know, what happens after the bounce out around one, that's like thermodynamics, right? So people knew all about that. But what they didn't quite realize was sort of the breadth of problems that could be solved with Monte Carlo. So it's sort of, they famously sort of said in one of these papers that, you know, just about everything can be solved with Monte Carlo, which didn't quite turn out to be 100% true, but I mean, it is somewhat true. So what you can do, for example, is not only solve, for example, like some simulations or whatever, but you can also like do optimization problems using simulated annealing. And like there's various different ways of using randomness to kind of like calculate things you might be interested in. But we're just going to deal here with more direct sort of random simulation, or sometimes called stochastic simulation. Yeah. So the simulator we're going to do is a discrete event simulator. So if you're a physicist like me, you would have been trained in like differential equations and you know, fluids and things which, you know, evolving smoothly and continuously across time, right? But a discrete events in physics, that's more like when two things collide and there's an impulse, that's a discrete event. Or in finance or something, like a transaction where like I give you money and you give me lollies or something. That's a transaction that happens at instant in time, right? Or in a discrete points in time. And so discrete event simulators work like this, and we're going to work with the concept of queuing. You know, someone walks into a shop and joins a queue, and someone's served and leaves the shop, and these happen at distinct points in time. They're the events. So they're events that happen at discrete times. So we're going to build a discrete event simulator engine, a relatively generic one, in fact, and you're going to use it to solve some queuing problems. So maybe I'll talk more about that like at the end or next lecture, but yeah. So we'll talk about pseudo-random numbers and how they're generated. We'll talk about, you know, specifically like how do you go from like some uniform bits that the computer generated to actual like a Gaussian distribution or something like that, right? So it's not straightforward. There's a few steps to get there, but we'll just go through them and I'll show you it's not magical or weird. It's just a little bit of math, right? And then we'll, during the course, we will talk a little bit about like what the various fields of Monte Carlo are, but we'll go more deep into the discrete event simulation. And we'll talk about this in the lectures, and you'll have lots of exposure to that in Project 2 and the pracs, I believe. And as a part of that, we're going to look at something called a heap data structure. So this is a priority queue. So if you have a whole bunch of things and you want to choose something which has the highest priority and then pluck it out, and then choose the next thing with the highest priority, pluck it out, all the time things are coming into the queue. This is the data structure that's sort of somehow best for this. And we'll talk about, you know, how you implement that in Julia, like how it works mathematically and like various things like that. Okay. So yeah, so that'll sort of lead into more kind of structured program, like more how would you say, yeah, how to make generic data structures in Julia, and also like we'll go into like how you create a more structured program in Julia using modules. Okay, so we're not going to go like the full shebang of how to make packages and release some open source and things like that. We'll just sort of have like how do you organize your code into modules and files and things so that it kind of makes sense. And like how once you have your code, a few little tips for benchmarking it, because you know if you're running these sort of simulations, obviously the more simulations you do, if they're random, the more simulations you do, the less statistical error you have. Okay, so this is a case where actually making your code faster means you actually get better or more accurate results. Yeah. So it's really important, and especially with my background in physics and also my current workplace where we're doing these style of discrete event simulations for businesses. So, and you'll also hear about Anna Ferglin, I think, has a lot of experience in this too. So it's always great to come to those what do we call it? Perspective seminars by the guest lecturers. Yeah. Yeah, cool. Excellent. So let's talk about random numbers. So there are actually some ways of using, for example, physics to make a truly random number. So I mentioned entropy before. So if you imagine you had like a silicon microcircuit, right? And some bits of it are at a certain temperature and some electrons are floating around randomly and stuff. It's sort of making some random voltages, and you can actually create an Intel and that create little devices on them which will pick up all the thermal fluctuations and sort of randomly spit out bits from that. Okay, so I won't go into how that works. We'll just mention that exists. But you might say that's not truly random. That's just like measuring the universe, right? So there's another interesting one, which is you can purchase a device which will make a quantum superposition of, say, A and B, and then collapse the quantum state into either A or B using a measurement. And that's kind of random in a very fundamental way, right? Well, I mean, technically it will cause some kind of macroscopic entanglement, but there's sort of no real way to unentangle that. So yeah, that's kind of cool that people build devices like that. Like we always, when I was an undergrad, we'd always like sort of joked about the idea, and then like 10 years later, they're selling it and stuff in Switzerland and stuff to banks that want true randomness and things like that. Yeah. But when we have a computer, we have like a computer that's used to dealing with zeros and ones, and you don't really have an operation which is like take a 0 and a 1 and produce a random bit. They're always like deterministic operations like and or, and adding things and subtracting things and multiplying things, and they always have an exact answer or a deterministic answer. So how do you use a deterministic machine to make something that appears random? Well, there's certain different ways of doing that. Like you may have come across chaos theory before, and so like you could start with, the final state of some thing might be quite uncorrelated to the initial state after some period in time, right? And so you can imagine the same thing holding for discrete mathematics when you have some space of bits and you do some operations or manipulation of the bits, and you end up with new bits, and what those bits are seemingly random or uncorrelated to what came in. For example, you might just change one of the input bits and 50% of the output bits are flipped, right? And 50% have stayed the same, which is sort of the maximum randomness you could expect, like decorrelation. Yeah. So if it's going to be deterministic, there's going to be some function which sort of goes from some inputs to some outputs. So you can imagine a random number generator in general has some hidden state in it. So it starts with some hidden state. It's called S. And what we're going to do with the computer is we're not going to just want to generate one random number, because we're going to have programs that want to generate millions and millions of them. So what we do is we evolve forward in time, and starting from some hidden state, what we do is we draw a random number out, and the hidden state will change a bit. Okay, and then we draw another random out, and the hidden state will change a bit. And draw another random out, and the hidden state will change a bit. So if we look at a very simple case, so the random number we're drawing is x. So we have x1, x2, x3, xn, and f is a function which goes from the hidden state and gives a random number and the new hidden state, s, n plus 1. Now, if you could imagine the simplest kind of random number generators, the s's and the x's are the same thing. Okay, so what that means is, given the last number you drew, random number you drew, there's a function which gives you a new random number. So like a bad example of such a function is xn plus 1 is xn plus 1, right? We could just increment the numbers, but that's not very random, right? But it's still a function f that obeys a formula like that. It's just we don't have randomness. We don't have everything's correlated kind of in an obvious way. So can we think of a better function f which will scramble things better? And like this is actually a rather important field in things like cryptography, but also just for mathematical simulation and things like how do we make things random enough. Okay, so obviously this function f is deterministic, which means that given S0, the first S, we can generate x1, and from that we can generate x2 and x3. And so those things are deterministic given the seed S0. So the seed is the name we give to S0. So a sequence of random numbers has a seed, and you might set that in a variety of ways, maybe just something the user types in, or maybe this instruction Intel provides to measure the thermal randomness, you might use that as the seed, because that instruction is very slow, so you don't want to use that all the time. Yeah. So what do we want out of F? Well, we want F to be something like a hash function, something which creates a lot, like scrambles everything quite well. So we want that the elements, say xi and xj, are sort of basically statistically independent. The ensemble that they form is some well-known thing. So for example, we might want to create a uniform distribution, you know, maybe of all 8-bit numbers, of all 16-bit numbers, of all 64-bit numbers, or something like that, right? And you know, the user obviously should know what that distribution and the range of that is. We don't want the sequence to sort of repeat itself too often. If it's deterministic, if you just add up the number of bits in S here, let's say S has m bits, then there's only 2 to the m possible states that S could have, right? So this, by definition, the sequence has to repeat itself at least once every 2 to the m. It has to have a cycle of at least, or at most, length 2 to the m. It'll get back to where it started, right? Because as soon as you get back to some number you had before, the cycle repeats because it's deterministic, right? But that doesn't mean all F's give something which cycles all the way around, right? You might have something which flips to 1 and then flips to 0 and flips to 1 and flips to 0, and the cycle length is just 2, right? So, you know, you want to choose an F where the cycle length is quite large. Ideally, it's larger than like 2 to the number of bits in X and things like that. So often the hidden state here will actually have quite a few more bits of data than the X's that you're trying to draw. And when you have that, you can actually get an extra nice thing, which is a really strong property, where it's basically almost impossible to determine what S is given the observations of X. So that's the sort of thing you want for cryptography, right? So you can have a server randomly, you know, connecting to different people, and you can't like somehow attack it by just sort of eavesdropping on the messages it's sent before, or then trying to guess what the next kind of, you know, key will be or something like that. Yeah, we won't go into cryptography or anything. I'm just mentioning it for completeness. So typically F is generally designed to produce some random number of bits. So some, here we got L bits, sorry. So if we have L bits, it produces a number between 0 and 2 to the L minus 1, so an unsigned integer, which we've covered. So typically something like power of 2, like 16, 32, or 64 sort of bits, you know, you typically use on the computer. That's the sort of target that we have for these Fs, all right? Now, if we have a random integer, we can easily convert that to a random float by just dividing it by the number of like 2 to the L, right? And then you'll get some number between 0 and 1. In fact, between 0 and slightly less than 1. So it's like, if you think of it as an interval, it's sort of closed at 0 and open at 1. But floating point division is a little bit slow, or integer division. So it's actually a bit better in practice to generate the mantissa of a floating point number. So if you remember the mantissas, or the significance of a floating point number, you know, you just sort of set the exponent. So it's like times 2 to the 0 or whatever, and you put in a random bits into the significant, into the mantissa. So that's actually relatively straightforward, and even Julia has an algorithm like this that you generate basically 52 random bits, and then all that with this number. Does anyone have any feeling for why this number would be this number? So that number happens to be 1023. So if you remember, the exponent of a floating point number is an offset integer, so it's like minus 1024 or something. And that's sort of just the way to get some number that's between 0 and 1. Well, actually, sorry. This will give you some number that's between 0 and 2, and 1 and 2, and then you subtract 1. Yeah. So you can actually dig into the Julia code and find where they do this. It looks exactly like that. That's cool. So Julia has also a this thing called RNG here. So normally you wouldn't bother specify this. By default, Julia has an object. So this RNG object is the one which stores the hidden state S. So inside RNG is this S thing. and it has some methods on it, so you can calculate the next random number and the next random state, like mutate the state or whatever. And so Julia will by default have one of these available. It will create one per thread of execution for you, so that it's sort of safe in a multi-thread program and things like this. Yeah. So sometimes it's useful to sort of explicitly create these things, and sometimes you just let Julia handle it for you, right? Because it's a bit easier. And also, again, sometimes you'll let Julia set the seed for you, or sometimes you'll set it yourself. Okay. So, so if you're trying to be scientific, if you're trying to do something scientific, it's really important to have reproducibility. So often knowing, and like maybe you have a paper or something, you might even tell people what the seed is, or like, you know, distribute code with your paper, which sort of sets the seed to a certain value, so that people can produce exactly the same results as you have in your paper, for example, if you're a researcher. But also, if you're just developing algorithms, you want to kind of like to be able to debug them and rerun them and see, you know, where your problems are. And there's other statistical reasons why you might want to share a seed between simulations. We'll talk about that too. So let's talk about a pseudo-random number generator. So first, what isn't a pseudo-random number generator? So it's not, pseudo-random doesn't just mean arbitrary or non-deterministic. So like if you, in Julia, you just create an undef array here. So that's this thing. What it will do is it'll grab some RAM using malloc, and whatever bits are there are going to go into your array, and that's that. Okay. So if I go to the terminal and type something like that in, what you can see is it's just malloc some RAM, which has been used by something else since I turned the computer on. And here's some bytes of data that are in there. It's just sort of random guff, right? Now that's not pseudo-random. That's sort of not even well defined what that is really, right? So you don't want to use stuff like that for your randomness, because sometimes you might run programs and they'll always be 0 because that RAM hasn't been used before. So it's a poor way of generating randomness. So one simple way of doing it is called a linear congruential, I can't even speak, congruential generator, the LCG. So this is where you like multiply, like start with an integer, you like multiply it by something and add something and then take it a modulo or something. And so typically if we're interested in like unsigned integers, we don't need to worry about the modulo because all the arithmetic addition and multiplication is modulo 2 to the L for an unsigned integer on the computer naturally. And so let's say you are trying to make, say, a 32-bit integer. You can choose nice parameters for A and C so that, for example, the cycle length is maximal and that the correlation between xn and xn plus 1 is sort of minimal, right? And so people like in the 60s and 70s, they would like publish books and papers and tables of good choices for A and C and M, so that people could use them in their physics simulations and various things. Yeah. So like here a very famous one, but it's more not a very well performing one, is one where you use these special numbers. C equals 1, A equals 69069. And you can make 32-bit. It's a randomness that way. And so like here's this implemented in Julia. So we create AC and M, and we create this next function, which is like this F from before. Remember this LCG is one of those simple ones where the hidden state is simply the value that we emitted the previous time. We're just going to generate a bunch of numbers. And so here's N is the iteration number, and XN is kind of the value that we drew. And you can kind of see it's sort of all over the place. If we make a histogram, the density is roughly uniform between 0 and 1. So it's a relatively good, it passes some basic statistical tests. But when you use this in more complicated things, you'll actually find it has little patterns and things, and actually using that in simulations can add a lot of bias and weird behavior to simulations. Okay, so it looks random, but this one's actually not random enough. It's very classic algorithm, but it's not something you'd recommend to use today. maybe on a much slower computer where that's all you could handle, then maybe that would be a suitable trade-off. So Julia has, more complicated algorithms. There's a whole field of study on what better sort of random number generator algorithms are. Things like Mersenne twisters and things. And Julia uses this algorithm called Shoshiro 256++. Relatively recently, it switched to this, and a few other languages use that or similar random number generators because they have good properties. Let's have a look. So what we can do is we can create this random number generator object manually with the seed. So the seed's 27. So just for clarity here, although I'm passing in like an integer, like a 64-bit integer in here, this thing actually has like 256 bits of randomness or hidden state in the inside. So you can, that's not sort of fully, you could specify a larger like 256-bit seed as well if you wanted to, but generally that's not necessary. So we can create a few random numbers out of it, right? And if we set the seed back, or we create a new random number generator with the same seed, we actually repeat the same pattern, right? So let's say we draw an integer from it and then a complex number. The same random number generator can make random bits, and those bits can be turned into integers or complex numbers or various things through the algorithms we'll talk about now. But like here's some just different kind of things you can do. But yeah, so basically using, this is where I'm just showing it's deterministic. If you do it again, you get the same things out. But there are often reasons like for creating, like explicitly creating and these RNG objects and managing them and reusing them or like creating fresh ones instead of reusing the old one and stuff. And so here's a reasonable example. So imagine a situation where you have what's called a drunken walk. So we're going to have a 2D sort of plane, and a person walks out of a bar, and he can stumble, he can walk forward, or he could walk back, or he could walk left, or he could walk right. That he sort of does this at random. Okay, so this is some sort of like stochastic Brownian motion kind of thing. And imagine we took that simulation, we wanted to simulate that, and we changed it up a bit where we had this parameter alpha, which in alpha means he moves sort of up and to the right a little bit, on average, a little bit more likely to move that direction. Okay, so what we're going to do is we're going to run this loop, basically just repeats this n times. It sort of flips, it picks some random number between 1 and 4 each time, and either moves left, up, right, or down, depending on the number. And then it biases it towards this number alpha. So that was one of the inputs here. N is the number of sort of steps we take in the simulation. Okay, so we take 5,000 steps by default. And then we allow the user to throw in one of these random number generators that they want to throw in. Okay, so we're going to look at a few different values of alpha, like that are close to each other, so like 0, 2 thousandths and 4 thousandths. And we're going to plot basically the effect. We're going to make some plots. We're going to look for how does alpha change the simulation, right? So the real question I have is, I've got this noisy system and I've got some parameters I control. What happens if I change the parameters a little? Okay. Now, if I use the same random numbers, the system's mostly going to follow the randomness the same way, and your little perturbations to alpha will kind of be comparable. But if you have different random number generators, the noise might overcome any difference in these small differences alpha might cause. Okay, so let's have a look. If we create fresh random number generators here with the same seed, and we vary alpha, what we can see is as alpha goes from 0 to 0.2 to 0.4, everything's moving in this direction up towards up and to the right. So we can sort of infer from these graphs that alpha moves things up and to the right. Okay. Now, if I use different seeds, this is the plot again. So if we change alpha, if I just had the plot on the right, I'd never had seen the plot on the left. I was just looking at the results on the right. And I asked you, oh, tell me the effects of alpha. Right. You can imagine you might come up with magic theories about what alpha does, right? It's all over the place. So the point is that the noise here is actually much larger than the signal. So if you're reusing the noise on the left, you can kind of, when you do subtractions and so on, you can kind of get a good signal out of that. But when you're using different noise on the right and then you do a subtraction, all you get out is noise. So sometimes it's actually quite useful to do this sort of thing. And so just sort of telling you all this because throughout your careers, when you're doing simulations and stuff, this is a really useful trick for reducing variance of your results and stuff. Yeah. Okay, so what we're going to do for the rest of this lecture is I'm going to talk about how you actually create distributions that you want, in Gaussians and various different types of distributions. Okay, so we've sort of spoken about how a computer can make some random bits. How do we turn random bits into a Gaussian or an exponential distribution, or Poissonian distribution, or some kind of weighted roll die roll or something. So let's just see. So what we got is, like I told you how to make a random number between 0 and 1. So on this set, right? So, or sometimes, you might call that as a distribution, you might call that uniform 0, 1. Okay. So, and the function in Julia to do that's called rand. So if I just type rand, it's just going to give me a bunch of different numbers between 0 and 1. Okay. So if you wanted to say create some uniform distribution between A and B, you could take that one between 0 and 1 and just scale it and offset it with a formula like this. Okay. So sometimes to create a distribution, it's quite obvious what to do given another distribution. You can transform the distribution, one distribution to another one. Okay. That's not too tricky. We could also take a number between 0 and 1 and try and pick a random bit out of this. It's probably not the most efficient way to do it, but you can. And so if that number is, for example, less than half, then you might say heads, and if it's less than half, you might say tails or something. Well, you could actually put in a probability here where it's not like a 50-50 chance of getting heads and tails, or true and false, or 0 and 1. It's some probability. So maybe it's 90% chance this and 10% chance that. And so, you might have the case that 90% of the time, this thing comes out as less than 0.9, and you get 1. And 10% of the time, this thing comes out between 0.9 and 1, and then you get the 0. Okay, so you can sort of see how P is changing this distribution from, from favoring 0 or 1 by whatever probability you want. So these are sort of like two basic ways of using randomness, and we're going to sort of continue building on this to get more complicated ones. So instead of tossing a coin, imagine rolling a dice. So there's multiple discrete outcomes. N, should I say N? Yeah, N. N discrete choices where the probability of any given one is a positive number and they all add up to 1, right? So you have some array of probabilities like this one, 0.1, 0.3, 0.2, 0.4, which adds up to 1. And that's our kind of probability distribution. Now you can come up with the cumulative probability distribution by doing something called a cumulative sum, okay? So let's say some vector was like that, right? And then I do like cum sum on that. What that does is it adds up. So the first element is just the first element. The second element is the first element plus the second one. The third element is whatever the last result is plus the third element. The fourth one is whatever that result was plus the fourth element, and so on. So you can efficiently create this cumulative sum just by iterating through the input array and creating an output array, right? And so that's the cum sum function in Julia. And so if these are probabilities, you can come up with a cumulative probability distribution by putting cum sum on it, right? And so obviously at the end, you want that number to be 1 because it's meant to be the sum of probabilities, right? Another thing is these numbers are always increasing or at least not decreasing because the probabilities can't be negative. All right, so this cumulative distribution is monotonic, and it's starts at 0 and ends at 1. Well, it doesn't. Well, in this case, it starts at the first element, but yeah, implicitly there's kind of like 0 chance of getting 0. So what we can do is we could create a function like this to draw from this distribution. Okay, so imagine you've done this cum sum and you're given this cumulative density function, probability function, all right, as an input. So, and you want to like pick an element given that you already have this cumulative distribution. So what you can do is you pick a number between 0 and 1, and then like if you look at this thing, if it's like less than 0.1, then you take the first one. If it's less than 0.4, you take the second one. Now let's have a look at that. What's the probability of getting the second one then? Well, we've already discarded or used up anything between 0 and 0.1 and assigned it here. And so the amount of that uniform distribution left is 30% of it left between 0.1 and 0.4 here. And that corresponds to that probability there. Okay. And so it's actually sort of the gaps in this distribution which gives the probabilities, or the deltas, or however you want to say that. All right. And so we just create this little for loop. We create a random number between 0 and 1. And then we find the first I such that R is larger than that. Is that correct? Must be correct. Generates the right plot. And oh, sorry. Yes, we find the first R where it's less than this, because if it's less than this, we go right down to return I. Yeah. And so if it's greater than that, then we increment I. Now, this function's not very robust. If this thing didn't add up to 1, sometimes this might like spiral off to infinity or have a bounds error or something. But you know, that's just a rough sketch of the kind of algorithm you'd use here. And you can kind of see if we call it 1,000,000 times. So we got this for here, and this is called a generator. So we generate 1,000,000 different samples from this, and then create a histogram of it with the plots library. The histogram looks like these blue lines, okay? And so you can see the first box is 0.1 and 0.3 and then 0.2 and then 0.4, which is exactly the sort of distribution we started with here. Yeah. So that's one way. So what were the ingredients here? We started with this cumulative distribution function, and then we ran this algorithm on it. Now, what this algorithm was really doing was actually going from a random number between 0 and 1 and projecting it sort of onto one of these based on those basics. Now, that sort of projection that I'm talking about is like inverting a function. So this cumulative distribution function's sort of like a function from 0, 1, 2, 1, 2, 3, or 4, right, to some real number between 0 and 1. The inverse of that is going from a real number between 0 and 1 and spitting out an integer 1, 2, 3, or 4. Okay, and so this is actually the algorithm that would generate that inverse function for you. Okay, well, given, sorry, R is generated randomly, but it could have been an input to this function instead of, and then it would, that's what it would be. Yeah. So if we know the CDF and we can find its inverse, we can actually use that to find more complicated distributions. Okay, so that's one way to do that. We'll get back to that. But while we're on the discrete stuff, I'll just talk a little bit about the binomial distribution. So sometimes, you know, if you know something about how distributions form mathematically, you can use that to come up with an algorithm to sample it. So just to remind you, the Bernoulli distribution is like flipping coins, heads or tails, right? The binomial distribution is like you do that like n times. You have a coin and you flip it 100 times. What's the probability you get 50 heads? What's the probability you get 79 heads? You know, and so on. So that's the sort of Bernoulli distribution. I think, have I lost the plot for that? I lost the plot. Yeah, so we'll look at the sort of the mean and standard deviation that comes out of that. So there's closed formulas for those. The mean is the number of times you do the trials and times the probability of getting the answer you want. So let's say we're counting heads, right? So the number of coin tosses times the probability of getting head, and the standard deviation comes with this formula, right? So if it's if p is a half, this is a half of square root of n. Okay. So let's just sort of come up with what those numbers should be. If you do 20 coin flips and there's a 30% chance of getting heads, then on average you're going to get 6 heads with a standard deviation of 2 point something. And if we do 1 million Monte Carlo samples, by sort of basically just every sample is like we actually do this experiment where we flip n coins and add up how many of them were heads explicitly, then we're going to get that same distribution, right? And so depending on your problem, this might be an efficient way of doing it, or it might be a really inefficient way of doing it, depending on the value of n and things like that. But it's all possible. And so if we do that Monte Carlo, so this is sort of a basic example of Monte Carlo, right? So if we do that, we get a mean and standard deviation, which is close to but not equal to the analytical result. Okay, so that's what you're always going to have. If I did that was for 1 million trials. If we were to do say 1,000 trials, you know, we might end up with a lot more noise. And if we were to do 1 billion trials, we might end up with less noise. You know, the noise roughly scales as 1 on the square root of n, right? If the statistics are well behaved, if it's not, doesn't have huge tails. Yeah. There's this really nice package in Julia called distributions, where you can get it to sort of almost analytically define distributions, and it defines samplers, so you can use the RAND function with them. And you can also get this mean and standard deviations directly out of the distributions. Okay, so these are the same analytical results as we had a little bit further up. Cool. So that's one way of doing it. Is it like you can imagine having some, like performing some experiment to do the binomial distribution. But another way to do it is going back to these CDS and actually directly coming up with almost a closed form algorithm for evaluating something. Okay, so let's look at an exponential distribution. So first, where does an exponential distribution come from? So this comes from events in time which are sort of uncorrelated, right? So if I have a radioactive source, say, and I pick up a Geiger counter, I'm a physicist, so I'm going to use these kind of examples, sorry. And the nucleuses in my radioactive source are kind of like popping and emitting neutrons or whatever every, you know, with some half-life, but they're sort of random and uncorrelated, right? If they're going off in a correlated fashion, that's really bad news. You don't want to be anywhere near that. That's a nuclear explosion. But if they're uncorrelated, yeah, then you know, then basically what happens is the radioactive, you know, products will just leave the area, and some of them will hit your Geiger counter. And so if you want to look at the sort of distribution in you know, how often you get a click on your Geiger counter, it follows this distribution where the time between 2 clicks on your Geiger counter is actually some exponential thing. So it's most likely that 2 clicks sort of come very close together in time. But you know, there's always some chance that there might be some gap, bigger and bigger gap, but that's a decreasing and decreasing chance. It becomes less and less likely. So that's these curves. So, and then as you can imagine, changing the sort of rate that these clicks are happening, lambda. So lambda, if this was some events are happening in time, like later on, we're going to have the example of people entering a shop to join a queue or something. Lambda has units of inverse time. Okay, so 1 on lambda would be like the half-life, for example, those kind of things, and but lambda itself is a rate, so it has units of like 1 on seconds or 1 on minutes or something. And so as you increase lambda, the curve here gets squished further to the left. You know, you're more likely to get smaller numbers coming out of this distribution, right? So lambda is inversely. So like the mean, for example, of these distributions is 1 on lambda, things like that. So now I'm just going to show you something which might seem a little magical, right? So the sampler for this is minus log of rand divided by lambda. Okay. Now I just spoke a little bit about this part. It might be somewhat obvious why, if you change lambda, if we look at these curves, we can get any other one of these curves just by scaling at left and right, and then renormalizing it. So it's a probability distribution. You know, integral is one, right? So if we have, say, a distribution for lambda equals 1, like a sample for lambda equals 1, we could turn that into a sample for some other value of lambda just by scaling it. That's where it comes from. But what's going on with this log bit? Well, you know, logs and exponentials are kind of related, so that gives us a bit of a clue. But like I said before, what we actually want to do is think about the cumulative distribution function and then invert it. And so then we can go from some random sample between 0 and 1 and project that onto one of the x's that we care about here, right? So if we have, so the CDF, you know, in continuous space is an integral of, so the CDF at x is the probability distribution, integral the probability distribution for all the smaller x's up to and including the x in question, right? So it's an integral from, say, that minus infinity up to some x. All right. Well, this would probably start at 0, and then, you know, maybe you'd go out to 1 or 2 or something. If you do that integral for this thing, you get curves that look like this. Okay. So depending on lambda, they look a bit different, but they all start at 0 and they all saturate at 1, and they all have this exponential kind of shape like that. Okay. But the sort of slope that you get here is 1 on lambda, and you know, the sort of decay time, you know, as they approach 1 is given by that rate. And so what we can do is, so we can come up with the formula for that, 1 minus x of like that formula there, right? And we can take that formula and come up with the inverse function, and it looks like this. Okay, so how do I do that? Like if I sort of swap these two, so x lambda x equals 1 minus CDF of x, right? Yeah. And then take the log of the exponent, get rid of the exponential, and divide by minus lambda. You get this formula there. Okay, so that's just some algebra. And then what we can note is if we imagine some random value r, which is equal to 1 minus some other random value p, and then r and p could share the same uniform distribution with 0 and 1. So this is just a trick that works in this one case, right? That these two things have the same distribution. So we don't really care about whether it's p, 1 minus p, or whether it's r, because they share the same distribution. And so you could imagine sampling with this formula there instead, where r is just some transformation of p, and then you get this formula here. So this r is this what you get out of rand, and then you do that. Okay. Now we talked about the Gaussian distribution just before we kind of like settle for the day. So the Gaussian distribution, there's another nice trick for that. Again, it involves a log, but there's square roots. You know, Gaussians, you know, that's e to the minus x squared on 2 kind of formula. So you're sort of seeing like the inverse of a square is a square root, the inverse of an exponential is a log. So you're sort of seeing some of the things you might expect to see here, but there's this wonderful cos thing going on there. Now, what on earth is that going on about? So this is called the Box-Muller algorithm transformation, and I'll show you what that's about. So if you've all done a calculus course, you might have been asked before to find the integral of a Gaussian. So let's take the Gaussian e to the minus x squared on 2, right? Why on 2? Because that's the one with standard deviation 1, right? So, and if you want to find that integral, the easiest way to do that is to square it and solve it in 2 dimensions. So you take that integral, you square it, and you rename the second variable y, and then this looks like a 2D Gaussian sort of integral. And then you convert that to polar coordinates, where x squared plus y squared is some radius squared, right? And then in polar coordinates, there's also some some angle between 0 and 2 pi. So we integrate the angle between 0 and 2 pi, the radius from 0 to infinity. We get this integral. Integral 0 to 2 pi of d theta is 2 pi. So we can just simplify that and put it there. Integral, and then we can do substitution to get, to sort of convert this using, we can make this substitution for r from little r to big R, and then d capital R is r times d little r, right? And so we can use integration by substitution to get this formula, which itself is just the number 1, okay? So we get 2 pi. And so the integral of the Gaussian is square root of 2 pi. That's how you do that. And we're going to use the same trick here with the Box-Muller algorithm. So like here we have this sort of 2D Gaussian distribution plotted, and you can see it's rotationally symmetric. So that's, you know, the theta doesn't really matter. So let's just imagine we did this transformation, and so x equals r cos theta and y equals r sine theta. So this is where that cos is coming from. What we want to do is we want to, instead of randomly sampling an x, we want to randomly sample an r and a theta and use that to generate an x and a y, okay? And so theta is easy to generate because it's rotationally symmetric, so you can just choose a random theta between 0 and 2 pi. R is a little bit more tricky because it follows this distribution here, but remember we could do this like we did with the integration by substitution. We can sort of think about this distribution, e to the minus r, and for the same reason as in the integral, we need to care about the width of the differentials. So we need to have this bit happening as well. And so drawing from this is sort of the same as drawing from this, and then kind of like squaring r and dividing by 2. Well, in this case, square rooting, halving big R and square rooting it, and that will give you little r. Okay. And so if this thing's an exponential distribution, we can sample it like that, right? And then we can plug that into a formula for little r, and we can get that. And then we can combine it with this cos theta thing here, and then we get the Box-Muller algorithm, which was this one. Okay. So it's just another sort of algebraic trick here to get this distribution. So if I create this as my random number generator for normals, and there's a rand n function built into Julia to do this, so you don't have to do this. We can sort of create like 1 million samples and make a histogram. You can see it's fitting the Gaussian very well. Okay. So it sort of seems a bit magical at first, but it's actually not too bad to derive. Another way of doing random number generation is of certain distributions. Let's say you had a distribution which was a circle centered at the origin of radius 1. What you can do here is something called rejection sampling. So it's just sample from a square. And then if the sample's outside the radius of that circle, just throw it away. Just throw it in the bin and draw another sample. Now, you can see the fraction of red here is only small, maybe 15% or something, right? So sometimes you might need to draw 2 samples or 3 samples or 4 samples, but on average, you know, you only have to sample 1 point something times to get a number. So it's actually a pretty efficient way of creating a sample within a square. And in fact, sometimes the Box-Muller algorithm is sort of implemented this way. You'd first do this kind of sampling, and from that generate a couple Gaussian numbers using a logarithm and stuff again. And I'll skip this thing about Poisson distribution because we're actually out of time. But it's kind of interesting. So that's it for today. On Monday, we're going to go pretty deep on event simulators, which is sort of something I work on, and something which is quite interesting and obviously very relevant to Project 2. So keep tuned. I hope you had fun today. Looking forward to the rest of the unit. Thanks. Thanks, guys.